Hi guys, welcome to my channel Sushruta. In the previous video, we have discussed about the valence bond theory postulates, and in this video we are going to discuss about applications of valence bond theory and even the demerits or limitations of valence bond theory. First, let's discuss about the applications of valence bond theory. In this, the first example is chlorine trifluoride ClF3. In ClF3, the central atom is chlorine. It is linked by covalent bonds with 3 fluorines. Look, the electronic configuration of chlorine is 1s2, 2s2, 2p6, 3s2, 3p5 and 3d0. This is vacant. This is the actual configuration. In ground state, the configuration is same. It won't change. 3s2, 3p5 and 3d. It is the outer shell now. So we are considering the outer shell. But in the excited state, the electron from P tends to move to 3D here. So we'll have 3 unpaired electrons. Sir, why should it go to excited state? Because to bind with 3 fluorines, it should have 3 unpaired electrons. In order to get 3 unpaired electrons, it has to move to the 3D shell in excited state. So look, the fluorine configuration is 1s2, 2s2, 2p5. The outer shell is 2s2, 2p5. In this, every fluorine outer orbital has 1 valence electron, 1 unpaired electron. See, these are 3 fluorines. The unpaired electrons of chlorine binds with 3 fluorines. So here, it is bonding with 3 fluorines now. These are bond pairs. So we have 3 bond pairs in ClF3, chlorine trifluoride, and lone pairs. Look, here we have already paired electrons in 3s and 3p. These paired electrons are known as lone pairs. Lone pairs electrons. So we have 3 bond pairs and 2 lone pairs. Next, 5 orbitals, that is 3s2, 3px2, 3py1, 3pz1 and 3d1. See, 3s2, we have 2 electrons, 3px, 3py, 3pz. Here we have 2 electrons. In 3px we have 2. Look, 3px 2. 3py 1 electron and 3pz 1 electron. 3d 1 electron. So totally we have 5 orbitals. Our electrons are filled in 5 outer orbitals of chlorine atom, intermixed to give 5 sp3d hybrid orbitals. See, here this is S, P1, P2, P3 and D. So S, P3 and D. This is the hybridization of ClF3. sp3d hybridization. So these 5 atomic orbitals intermix and form 5 sp3d molecular or hybrid orbitals. Got the point? For this point, if anybody didn't watch the previous video, please watch it. You can understand better. Next, half-filled 2pz orbital of 3 fluorine atoms overlaps with 3 half-filled sp3d orbitals of chlorine atom to form 3 sp3d p sigma bonds. Yes, see, here 2px, 2py and 2pz. The 2pz, the electron present in the 2pz binds with the p, 3p of chlorine, right? So these 2pz orbitals bind with the 3p and 3d and forms strong sigma bonds. This forms strong sigma bonds. This point refers to that. The expected geometry for sp3d hybridization is trigonal bipyramidal. Yes. When we see sp3d hybridization means, first the parent geometry comes into our mind, that is trigonal bipyramidal. But we have 2 lone pairs here, one and the other one. So totally we have 2 lone pairs. So, but due to the presence of 2 lone pairs and the repulsion caused by the lone pairs. If the lone pairs are both present at the same place, they repel. Same charges repel now. and the shape of the molecule turns to be T-shaped structure. Look, this will be the structure. Due to this lone pairs, the repulsions occur. Lone pair repulsions occur. So that the shape of the molecule changes. So instead of trigonal bipyramidal, the formed shape is T-shaped structure. See, this is T-shaped structure. The bond angle is 175 degrees. That means FClF. It is not 180 degrees, it is 175. What I mean to say is this angle like this, it should become 175. Here small bends occur at these fluorines, I mean the axial fluorines. Due to these repulsions, lone pair repulsions, small bending occurs. So the angle decreases and 175 degrees occur. It will not come as 180 degrees. And the FClF angle is 87.5 degrees. See, this angle will be 87.5 degrees. It is not 90 degrees. It is less than 90 degrees. Due to the bending of this fluorine. This fluorine will bend towards this side. Due to these repulsions, as I said before. And 2ClF axial bonds length is 1.698 angstroms. See, the axial bonds of fluorine, ClF, these bonds length is 169.8 picometers or 1.698 angstroms. All are same, but picometers means 10 power minus 12 meters and angstroms means 10 power minus 10 meters. So small alterations occur in the decimal, that's it. But the length is 1.698 angstroms for axial bonds. And 1 ClF equatorial bond length is 1.598 angstroms. This will be the equatorial fluorine and its bond length is 159.8 picometers or 1.598 angstroms. Both are same. This is the T-shaped structure and this structure was also T-shaped. It was drawn to explain the angles and bond lengths. That's it. Next, the second example is nickel tetracarbonyl, NiCO4. Here, in NiCO4, the nickel has zero oxidation state. Yes. So, first, let's see the electronic configuration of nickel. 1s2, 2s2, 2p6, 3s2, 3p6, 3d8, 4s2. So, 28 is the atomic number of nickel. So, this is the electronic configuration and 4p will be vacant. The ground state is 3d8, 4s2 and 4p0. The bonds will be filled in this manner. But here we have the carbonyl group. It is a strong field ligand. In strong field ligands, the bonds pair up and move towards. So, in order to accommodate 4 electron pairs donated by 4 carbonyl groups, nickel must have vacant orbitals, which is achieved by pairing of 3d orbitals. Yes, there are 4 carbonyl groups. So, to accept electrons from 4 carbonyl groups, to accommodate those electrons, here the electron pairing should take place, especially in 3d. These electrons transfer occur and pairing will be done. This is due to strong field ligand. Yes, carbonyl is strong field ligand, CO. Remember it, you will get it in coordination chemistry. Next, see, this is the perfect structure. Look, these electrons are given a different color. These are indicated in cross marks to let you know that these electrons are accommodated here by carbonyl groups, 4 carbonyl groups. That means due to the presence of strong field ligand, the electrons which are present initially in 4s transferred to 3d and there the electron pairing has been occurred. And here the sp3 hybridization is formed. sp3 hybridization. So thus NiCO4 is having sp3 hybridization. sp3 hybridization. So shape of NiCO4 is tetrahedral. Yes, we all know. The parental geometry for sp3 hybridization is tetrahedral. It's tetrahedral. NiCO4 is diamagnetic because it has all electron paired. Yes, look here. There is not even a single electron unpaired. All electrons are paired. So it will be diamagnetic in nature. This is the structure of NiCO4, nickel tetracarbonyl, tetrahedral shape, right? But see, why I indicated these bonds with arrows? Everybody will have a doubt in their minds. Look, I want to clarify here your single thing. That is, these bonds are coordinate covalent bonds, not covalent bonds. These are coordinate covalent bonds because, see, here both the electrons have come from carbonyl groups in S and P3. So, both the electrons are here from carbonyl group. There is no sharing of electrons in between nickel and carbonyl. So, that is the reason 4 coordinate covalent bonds are formed. Remember this point, okay? It will come in your competitive exams too. The possibility of dsp2 hybridization of nickel in NiCO4 is discarded by fact that NiCO4 is tetrahedral. Yes, here dsp2 hybridization will not occur because we can see here the tetrahedral shape determines it. And finally, the limitations of valence bond theory. Failure to explain the tetravalency exhibited by carbon. Carbon has its tetravalency, but this theory it cannot explain the tetravalency exhibited by the carbon. It is a failure. This theory assumes that electrons are present in specific areas. That means electrons are located in specific areas, but they are also delocalized electrons. So this is again, this point differs. It is a failure. No distinction between weak and strong ligands. Yes, there should be a distinction. The difference should be shown between weak and strong field ligands, but it did not show. Valence bond theory. No explanation for the color exhibited by coordination compounds. Paramagnetic compounds always exhibit color, but that explanation was not given by valence bond theory. So, scientists mostly they prefer molecular orbital theory for chemical bonding. That's it for today, guys. If you like my video, please like, share and subscribe to my channel Sushruta. Meet you in the next video. Bye bye, guys.